Hello AP Stat. Welcome back to the last installment of Chapter 9, Re-expressing Data. We're going to look at one more approach our textbook gives us called Attack of the Logs. Yes, that is literally what our textbook calls it, and I tried to one-up the textbook with this ultra-cheesy Star Wars reference, complete with Comic Sans font. So, Attack of the Logs consists of using the logarithm rather liberally. There are three ways we can use logarithms to transform data, one of which we will call the exponential, we have already used. We're also going to learn logarithmic transformation and power transformation. So, first, exponential, the one that you've seen before, is x log y. We transform the y values. This what we referred to as 0 before. Transform the y values with a logarithm. That is useful for plots that follow exponential growth patterns or decay patterns. The pattern to the left, of course, is exponential growth. The pattern to the right is exponential decay. So the idea is we want to undo the y with a logarithm, because a logarithm can undo an exponent. All right, a logarithm can undo an exponent. So if we want to undo y values that follow an exponential pattern, let's just undo that with a logarithm. Next, we have the logarithmic transformation. If our function follows a logarithmic pattern itself, it's better to just undo that logarithmic pattern in the y values by applying a logarithm to the x values. If the y value follows a logarithmic pattern like we see right here, why not just apply a log to the x and hope it balances out? Well, it usually does. The transformation is useful for plots that follow a logarithmic function. So if I log the y value, that's good for exponentials that look like this. Logarithmic pattern is good for this sort of thing, or reflection of this sort of thing in the x-axis, but that is very, very rare. Finally, we have the power transformation. I'm going to make a confession here. I don't know why this works, but it does. A transformation that's useful for power functions like ax squared, ax cubed, a being some stand-in for a constant, ax squared, ax cubed, and so on. If your data follow a power function, then you're going to want to log both x and y and see what happens. And that is a nice finale to Attack of the Logs. So now we're going to apply each of these attacks, if you will, on a set of data and see what happens. So we're going to find the best re-expression for this set of data from the University of Minnesota. Here is a table that gives the number of loaves of bread produced by the given number of bakers. Clearly, the data don't follow a linear pattern. So first, we're going to proceed down the ladder of powers and or attack of the logs until the re-expression fits a linear pattern. Check the residuals for a pattern to make sure. Now we're going to jump right to the chase. You can try ladder of powers on this one, but the best re-expression is probably an attack of the logs re-expression. And once you see the original plot of these data, you will understand why. Next, we're going to compute the equation of the regression line for these data and approximate how many loaves of bread 7 bakers would bake. So we'll use our re-expressed data to do a computation, which will involve a bit of algebra. Get pumped. So here's the original scatter plot. If I were to apply the exponential, which is we log the y values, well, we just make things worse, all right? Why? Because these data seem to follow a logarithmic pattern, not an exponential pattern. So if we take a logarithmic pattern and further logarithm the y values, we're just going to exaggerate the problem, which is exactly what happened. So we have this right here, log x and y. That would be our logarithmic transformation, which should work. If our original data follow a logarithmic pattern, why don't we just log the x values, because the y values already follow a logarithmic pattern. Maybe that'll balance out. And this one kind of does. You'll notice we get a negative x value over here. That's okay. Logarithms cannot work with negative inputs, but they do sometimes produce negative outputs. That's not a problem. Okay, so this one should work best according to our principles for attack of the logs, and in fact it does. Just to cover our bases here, we're going to use the power transformation. This is definitely not power. This is definitely logarithm going on. But if we were to try the power transformation, it's not bad. But if you look closely, it's not quite as good as the logarithmic. So we're going to stick with our logarithmic transformation. So let's check this residuals plot. First thing we need to do is compute our regression equation. And the way we're going to do that is we're going to take our x values and apply that logarithmic transformation. We're going to log our x values. So I'm going to hover over list 3, and I'm going to say log of list 1. So my new x values list is going to be list 3. Let's now go into, we got to do the regression line first. So I'm going to say stat. We're going to go to tests, one-stop shop. We got to do linreg t-test. And we're going to change list 1 to list 3. That's our set of x values after the logarithmic transformation. Y list is still L2. And we go all the way down to calculate. And there we have it. I just want you to appreciate how good this regression line is. Look at r squared and r. That is a great regression line. Our data appeared to fit the line well. Let's make sure, though, that the residual plot agrees with these awesome results for r squared and r. So now we're going to check out this residuals plot. I'm going to go to second, stat plot. And I want to make sure that I am plotting list 3 against the residuals. I have this already put into the calculator here. But just to recall, second list number 7 gets you your residuals. Okay, so now what I'm going to do is go to zoom. Number 9 is stat, and we have this action going on. We have there is still a bit of a pattern here, but it's a little more chaotic than what we had before. This is a tough set of data to work with, but we also have a small number of values, so we need to take that into consideration. Is there an obvious arc here? Well, it's a bit interrupted over here. There is a bit of a pattern on the right, so it's not perfect, but at least it's better than what we had before. So now that we've checked the residuals plot and got at least a more satisfying result than we would have had without the transformation, we're going to go to step 2, which is compute the equation of the regression line. We'll just get that from the calculator for these data and approximate how many loaves of bread 7 bakers would bake. Now you will notice we're finding a result for 7 bakers, and 7 is outside of the interval 1 to 6. So technically this is extrapolation, so we will take our result with a grain of salt. So here is the regression line. You could get this from your linreg t-test. It would be the number of loaves that we predict is equal to, here's your b sub 0, here's your b sub 1, and then it's not just the number of bakers. Remember, we applied a log to the x values for our logarithmic transformation. So it's the log of the number of bakers. Here's the evaluation. We substitute 7 bakers, and we get 1,186 approximately number of loaves. So the model predicts 7 bakers would produce 1,186 loaves, just about. And as I said, this is technically extrapolation, so we will take this result with a grain of salt. Let's try one more problem to see if we've mastered the skill of data re-expression. We're going to consider the table below with data that describes the relationship between the gauge and diameter for earrings. So gauge is going to be our horizontal axis variable, diameter would be our vertical axis variable, so we have the explanatory and response variable there. We're going to proceed down the ladder of powers and or attack of the logs. This time we'll open it up to all possibilities until the re-expression fits a linear pattern. And there is going to be a best outcome here. And the residuals are going to look great. I'm just going to let you know ahead of time. Check the residuals for patterns to make sure. We will certainly do that. Then compute the diameter of a 3-gauge earring. So try some re-expressions after making a scatter plot of these data. It'll look like a couple of possibilities might work. Try a few, see what works best. Feel free to unpause the video once you think you have found the best re-expression. Okay, I'll assume we're ready to continue. So our original data looked kind of like this, which made me think of a couple possibilities. Our data kind of resembled a 1 over x sort of character. And I thought, okay, maybe opposite reciprocal square root, what we referred to as -1/2. It also kind of resembled an exponential decay, so maybe an exponential transformation, which in another context we referred to as 0, applying a logarithm to the y value. And this second transformation is definitely the winner. So now what we're going to do is check the residuals, and as I said, the residuals look great. So the residuals are awesome. No issues here. We don't have to play fast and loose with the residuals and make excuses this time. This one is excellent. Okay, so here we go. This is the model we're going to be using. Remember, we applied a logarithm to the predicted y value. So the log of predicted diameter is equal to, here's my B0, here's my B1, times the gauge of the earring. So we're trying to predict the diameter of a 3-gauge earring. If you saw that in the problem, 3-gauge earring. So we'd substitute 3 for the gauge, and we get this value. And then just as a reminder, to get ourselves out of a logarithm, you may remember from algebra, you consider the base of the logarithm. If there's no visible base, then the base is 10. And so we would exponentiate with a base of 10 on each side. The predicted diameter, therefore, is equal to 10 to this messy exponent, which turns out to be about 5.6. So the model predicts a 3-gauge earring would have a diameter of 5.6 millimeters. And I predict you are going to have some homework to do. Have fun with this one. Have fun with these data re-expressions. See you soon.